Okay, we'll go ahead and get started here. Some of you might be wrapping this up and writing these down. Let's see here. Before we get too far, just one. I need to take attendance quick, so I'm just going to go ahead and hit pause here, and we'll be right back. Okay, so as we look at this then, okay, in case you can't read if you're tuning in later, it says how much power. As some of you know, they're continuing the school expansion here, and they just hauled a payloader in this morning. They got to get all the dirt out of there, so we got dump trucks coming back in, and that's what we're alluding to. So I just looked outside and thought, maybe we could make a problem out of that quick. I don't know how accurate this is, because one of the things we said, we try to make sense of the natural world, and you can do that sometimes by just looking outside, okay? So how much power does a payloader have if it lifts a load of dirt 3.4 meters, and I don't know how high that would be. Of course, I think into the dump truck would probably be every bit of 9 feet, okay? So that would be about 3 meters, but then you have to lift it higher than the back of the truck so you don't damage your equipment as you are dumping the load of dirt or gravel, well, it would be dirt, into the back of the truck. So if that's 3.4 meters high, and not that you'd be standing there with a stopwatch, we're just trying to guess and try to maybe come up with a problem that would make sense. So then the dirt inside that bucket of the payloader, okay, might have a mass of 14,240 kilograms. Again, no idea, just making a guess on that to hopefully come up with something that would actually make sense. Because not only would or could we solve for power, but once you do that, you could take that one step further and solve for what?
Force.
No, we would already do that.
Horsepower.
Yeah, you could solve for horsepower then, okay? Then this bottom one is one that is brand new. We talked a little bit about this yesterday. Poor Jack, okay, gets saved by Rose by swinging the axe and busting the chain, and we said, well, not likely that would happen. But anyway, so in the trunk of a tree, when a lumberjack is going to swing its axe, okay, you're going to meet a certain amount of resistance into that of the trunk of the tree as well. So not only do you meet that resistance, but that will also travel into the trunk of the tree. And it's not that when that axe goes in there, how does it keep going further and further and further in? Is it just moving? It removes material as you go, correct? You see chips of, let's say, of that wood flying out of there, especially if it is a sharp axe. And I would certainly think that that's probably something that was not only done on a daily basis, but probably maybe 2 or 3 times a day as you're possibly being a lumberjack back in, you could say, the late, let's say, 18th century, 19th century. So if we say the 19th century, late in that century, approximately what time frame might that be? Now, think about that for a moment. The late 19th century. Anybody just have a guess?
1980?
Well, then that would be a little too recent.
1960.
Nope, that's still the late 19th century.
1900?
Okay, you're getting a little closer when you say 1900.
1880.
Yeah, so maybe 1870s to maybe the 1890s would be part of the 19th century, because you got to count the first century from what we call Year of Our Lord. I think that's what you call Anno Dominion. So that's when we say not recorded time, but how we measure time in years. So that first year 1 to 100 would be your first century. So then when you get to the 100s, 101 to 199, that would be your second century, and so on. And that's why it's one of those things, it's kind of a trick question. But regardless, while swinging this axe, a lumberjack exerts 48 newtons on a trunk, and the resistance of the trunk is maybe 4.18 meters, and the axe moves 0.11 meters. It should say from the resistance. That's something that I didn't quite get into there. We'll make sense of that. So how far did they swing the axe? This is a new problem. So now that we've read both of them, now I think we're about 28 and 29 times. We're about that far. Okay? So for the 28th time, or 29th, you've read the problem. What should we do? Okay? Write down what we have. Okay? So in this top one, we'll go ahead and do that one first, just because this is based off of familiar material, but this would probably be a little difficult just looking at it because there just isn't very many numbers in it. And I don't know, we just wrapped up the zoology class. I thought, I got to get something down here. They just started writing and trying to come up with some numbers that we could maybe rationalize and make sense. Okay, so what do we know in this problem?
How much power does the bill
but we don't know that. That's why I said,
Yeah,
what do we know? Yes.
It has a mass of 14,200.
Right. So we know the mass. Okay. And you can just tell me. What else do we know?
The distance is 3.40 meters.
Time is 30 seconds.
Okay. Not quite.
30 seconds.
So then we want that. Okay? So now whether you have your zigzag or whatever it is you put over top of that if you choose to, there's not a whole lot of information to go off, is there? But for some of us farmers, or if you've ever worked with, okay, they say a loader tractor, skid loader, payloader, any one of those, okay? Is anyone really good at just scraping straight across the ground without digging into the ground? That's something that I always had a problem with as well. But now, okay, I'm just looking out in the crowd, and I think we can maybe, I'm not saying pick on yourself or even yourself, but now if you are having a loader tractor and you let the hydraulics down on that, aren't you able to push that lever all the way forward? Then the bucket comes down to the ground, and then it stops once it reaches resistance on the ground. Have you ever heard of that or done that before? I think it's called a float device, okay? So then you press the hydraulic lever in, you push it all the way forward, the bucket comes down. Once it reaches resistance, it stops. It doesn't lift the front tires off the ground. But you can do that. You just wouldn't push it all the way forward and let it stick. You would let it hit the ground. Then if you kept pressing that lever forward, now that bucket is pushing down on the ground, your front wheels come off, and then you're really going to start digging into the ground. But I wasn't the best at it either, probably because I didn't have it tipped just right maybe as well. But what do we need to know to solve for power? Okay, so we need to know what the work is, and you would need to know the force. Yep.
horsepower?
Okay, well, we'd probably make that intuitive leap a little later, horsepower. Okay? Is there anything else? Now, keep in mind, look at this guy. What are we possibly missing?
An A,
What is that A?
9.8.
It could be, but the main idea is we're talking about an acceleration here.
Yeah.
And when we look at this, I just ran out of time because I wanted to get this problem down too. We're going to make a presumption here that that payloader went across the ground, it hit the pile, okay? Then the operator pulls the lever back. So what we would presume then is that as they're lifting all that mass up to this height in that amount of time, that how fast was that going then? We're making a presumption. Okay, so it hit the pile, okay? What's it doing right now?
Lifting. Or
Someone said nothing. Right, we're not doing anything, are we? So how fast is that moving?
0.
Right, so that must mean we have what type of a velocity here then?
I.
Okay? We're also missing one more variable here.
Final velocity.
Because why are you right?
Because it didn't start first, so it was an initial velocity. But to find the final velocity, we do distance divided by time.
That is 100% correct. Okay, so we also have to find this one. Now, this is why we go over these. For people who choose not to follow along, I can't imagine how difficult this would be. But I think we would agree it's possibly of your own making if you choose to do that. We'd have a better idea when our evaluations show up on how to do this. Okay, so you said correctly, we need to find that final velocity. So let's go ahead and do that. So how do we find that final velocity?
3.40 divided by 0.30.
So we got a distance and divided by a time. So our final velocity then is,
11.3.
okay? And that's meters per second. Okay, so we've got our start. So
There wasn't a 0 for.
I tack it on the end. I just do that by habit. Yeah. So just by habit, I'm sorry. If I belt or burp, it's just by habit. I say, excuse me. That's just what I do. I don't know. But that's just like putting this on. That's just what I do. So an acceleration then, how do we find that?
We do A equals, and on the right side we put 11.33 minus 0.
Good morning.
Okay, just a moment here. So now, we got our 11.33, and what are we going to divide that by?
0.30.
0.30. So what is our acceleration then?
37.76.
Oops.
Do we have to round them up?
Yeah, if there's three, I always go to the nearest hundredth, which is 2 decimal places. Okay? 37.76. Okay. Meters per second squared. So if it's 0.75, 0.74, whatever it is you got on your calculator, somewhere around 37.76. It doesn't have to be there exactly, but it should be within that vicinity. Okay.
If I round it up, it would be 37.87.
Okay.
I only just kept.
You can go ahead and use that number. Okay. So now we have our acceleration. There again, just keep moving right up the ladder. Okay. So what that means then, now we have our acceleration, and what would we solve for next?
4.
Okay, so I think we can get rid of, because we've found those, so we can get rid of this or these. So what does our force equal now? And our mass is, according to our setup, 14,240 times what? Okay, so what is our force now? It's going to be a really, really big number.
537,702.4.
Okay, does that look about right to other individuals? Okay, well,
It's 537,702.4.
okay, so then I just put that 0 on at the end. I just do that by habit. 537,702 point, yeah, so that's what we get. So that's labeled in newtons now. Okay. So then notice we can get rid of some of this content because we've already calculated those. So what is the next thing we will calculate?
Work.
Isn't that what this is? Isn't this work? Yeah, yes it is. But okay. So what does our work equal?
Force times distance.
So we just found the force, which is 537,702.40. And we're going to multiply that by what? You said the distance, correct?
Yeah.
Which is 3.40. Notice that these numbers, they continually get bigger and bigger and bigger. So we can take this number that we just calculated times 3.40. And rather than someone reading this off, you tell me if this is not correct. 182.8188.16 joules.
Yeah.
Okay? So now that we've calculated that, we can get rid of this. Okay? So again, we just go right up the ladder. We found our work. Finally, how do we find our power? So we can take this number, and since we're running out of space, you can just hit divided by our time, which is 0.30. So our power then equals 609,396, 05. Now there's a decimal after this 0, correct? Yeah. Okay. So this power then is labeled in what?
I didn't get that.
Labeled in watts. Okay. I would think it's probably somewhere close to that. Okay. Then finally, that answers this question, but maybe we want to know how much horsepower does that payloader have? So approximately, what would it have to solve for that? How would we find that?
Power and 746.
So if we divide this number by 746, yeah, I doubt that it has 8,000 horsepower. That would be a little much. But again, we just wrote that problem up just really, really quickly. So that would be a lot. I think maybe some tugboats might have 8,000 horsepower, but probably not a payloader. But you went where the numbers led you to. Okay? All right. So what I want to do now then,
Hey, Gresham,
yes.
that's why I'm vocal.
Okay. So we will start with this problem on Monday. So as we look at next week's schedule, okay, it says your third paper, which we have our second one, which is due today, correct? correct? Yes. Okay. Okay, so again, as we look at that schedule, weather permitting on Tuesday, okay? We got to see once what the weather is. We've been talking about this activity. So we have a couple sleds that we put some weights on and that we pull. Just keep track of the time. And then you can calculate your individual horsepower. Ideally, we'll be finishing this chapter on Wednesday. So we'll have these handed back sometime early next week because a lot of you are working on these together, and that's what we encourage is cooperative learning. But as we all know, that eventually you're going to be responsible for this material on your own, okay? So if you're getting help from other students, keep doing that. That's your cooperative learning. But we all know that you're responsible for this on your own. Any questions about how we're proceeding to next week? And one of the reasons that we're doing it this way is hopefully the weather's good, that I don't know, some of you maybe already have it in your mind that Tuesday night we want to take the spectator bus to the game, and that's fine. But that's why we're going to try to do that during the day rather than the following day. Okay. So again, any questions about next week as we're moving forward? Okay, so that's all I have. We will catch up to you next time.